Hi, everyone. This is Team 32. I'm Tim, and my teammates include Xing Yang, Yilin, and Carida. Our topic is this important distance between two stereo cameras. So in a perfect world, two cameras can produce a 3D depth map. The pixel displacement between two images is also called disparity map. It can be calculated with some mathematical computation algorithm, but of course, deep learning model can do better in this image task. When we look into the deep learning model, intuitively, we think that the distance between two cameras are critical to find the disparity map, but it is never an input. We start to think that the distance is somehow encoded in the model's parameter and wonder what happened when fine-tuning the model for another dataset. We conduct a series of experiments, and my teammates will introduce them right now.
The machine learning model we use to evaluate this idea is called a pyramid stereo matching network, or PSMNet in short. This net first passes the stereo images through two weight sharing pipelines, which contains CNN module, spatial period pooling module, and final convolution layer. The left and right features are then used to construct a 4D cost volume. The 4 dimensions represent the image width, height, feature channels, and disparity. Then this 4D cost volume is fed into 3D CNN. We use stack hourglass model, which is basically an enhanced ResNet in our experiments. Next slide. In this work, we use 3 data sets. The first is called SynFlow, which is a large synthetic data set. The second is called Kitty, which is a popular real-world data set. And the third one is our own data set we generate using the Unreal game engine. In this way, we can control the camera distances. So we choose the 100 positions, and at each position, we took 6 images called right image and left 0 to left 4. Next slide. Then we conduct the first experiment by training the model using 1 image pairs between right image and left 0 image. And then we apply the trained module on other image pairs, for example, between right image and left 1 image. We observe that the loss and the error rate are terrible for other image pairs. Next slide.
So to find out why the model does not work well on our generated dataset, we decide to look at some important layers in the network. The author claims that the SPP plays an important role in feature extraction. So we start with our first experiment by freezing some layers in the SPP module. There are 4 convolutional layers in the SPP with different kernel sizes. So we start our experiment with no layers frozen, and then we gradually freeze 1 layer at a time. The results shows that the original model and the models with frozen layers took almost the same epochs to converge, and the same accuracy results. Next slide, please. And next, we focused on the stack hourglass module, since the author claims it is critical when upscaling the extracted features. After freezing the hourglass module, we find that the model loses accuracy significantly. Thus, we conclude that the SPP is general enough and do not have to be retrained, but the hourglass model might be the one that actually encoding the distance. Next slide, please. Our next experiment is to retrain the model of our generated dataset. We find that the retrain process is not linear with a change of distance. In fact, for our experiment, it took the similar epochs to achieve this same accuracy. Next slide.
To verify the conclusion from our experiment, we compared the kernel weights between the network trained on SynFlow and the one fine-tuned using Kitty 2015. We first fine-tuned a pre-trained PSMNet model that was trained using SynFlow on the Kitty 2015 dataset for 300 epochs. Afterwards, we compared the kernel weight distribution of both models via histogram. From the histogram, we can see that the model trained on SynFlow in orange and the model fine-tuned using Kitty 2015 in red have similar kernel weight distribution for all layers in the CNN. Additionally, both models have similar kernel weight distributions in the spatial pyramid pooling module. as well as in diffusion layers before cost volume generation. Closer examination indicated that weight distribution differences occurred in the stacked hourglass. The light blue line shows the weight distribution for the model trained on SeamFlow, while the dark blue line shows the weight distribution for the model fine-tuned on KITTI 2015. From this, we can conclude that the distance is encoded in the pyramid stereo matching network. The network is sensitive to image pairs taken from different distances. Fine-tuning the models can migrate the ability to predict disparity fairly well. Experiments indicate that spatial pyramid pooling module can be used for general feature extraction, but the stack hourglass, which upsamples, encodes the distance and must be retrained. The retraining process takes similar number of epochs to achieve similar accuracy and is not as linear with the change of distance as we thought. Thank you for listening to our presentation.